Okay, so today we're going to talk about covalent bonding orbitals and we're going to talk about the valence bond theory. Now, disclaimer before we start, okay, because second period freaked out on me, third period we were good, okay, we bonded. Joke, joke. All right, anyway, it was funny. All right, so anyway, second period freaked out, third period got it. Here's what I need you to realize. All I need you to really understand today is how to get the answer. I don't need you to understand the why. Okay? Am I going to teach you the why? Yes. Okay? Are you going to understand the why? Some of you aren't. Is it okay? Yes, it's okay. Because how to get the answer? Ridiculously easy. Everybody can get the answer. In fact, if anybody misses this answer on the quiz we're either going to take today or tomorrow, depending on time, Snellick is going to be highly upset because hybridization is very easy on how to get the answer. And guess what? The only thing they're going to ask you on the AP exam that has to do with the hybridization is the answer. They never ask you to explain hybridization. All you have to do is give them the answer. So that should be a comforting thing. Are we all comforted by this?
Absolutely.
That the answer is easy to find and the answer is easy to get. So are we going to freak out today if we don't understand the why? No. Okay? Now, are we going to try to understand the why? Yes, because it just makes us well-rounded in chemistry knowledge. Okay? But we're okay if we don't. Do we all understand my disclaimer?
Yes, ma'am.
Yes? And we're ready to go.
Mhm.
Yes. Yes. Okay. And here's also the good news. We're finished with the unit as far as materials today. So nothing else new will be taught. All right? Tomorrow we're going to review. We're going to do a review on shapes. And I think maybe you should learn all of the shapes and it would make it a little bit better because there's only a couple more. So I'm going to do a review sheet on shapes and we may work on a few for your response. Thursday we're going to do an aspirin synthesis lab that you do not have to do a lab report for. We're just doing the lab to do the lab. It really has nothing to do with what we're doing. I've just always wanted to try Thursday. I've always wanted to try the aspirin synthesis lab, so we're going to make aspirin, and then we're going to analyze it and see how well we made the aspirin. So that's what we're going to do.
Can we sell it?
That's what we're going to do Thursday. Huh?
We can pass it out if we make it. Here, try some.
Try some aspirin. Okay. So that's what we are going to do. Excuse me. Thank you. All right. That's what we're going to do in lab on Thursday. And then it looks like we'll probably test either Monday, Tuesday, Wednesday.
Tuesday, Wednesday.
Okay. So,
It's never
Thursday,
been
Friday,
come
that's
back
fine.
from a weekend.
okay, so Tuesday, Wednesday. So we'll multiple choice Tuesday, we'll free response Wednesday. Yes?
Yes, no.
Yes. Knowledge. Knowledge.
These are really sweet.
So we good to go? Yeah. All right, here we go.
Super sweet.
So, covalent bonding orbitals. We've already talked about the VSEPR theory. Okay, we've already talked about how those lone pairs bend bond angles. We've already talked about how we get the shape. We've already talked about why they bonded, but we've never really thought about, like, does it make sense? Like, does it make sense that CH4 is tetrahedral and all of the bond angles are 109.5? No,
Not really.
it doesn't make sense at all. And if you think about it, it really doesn't make sense. Okay? So, let's talk about methane. Okay, let's remember a little organic chemistry from last year. Naming organic, lesson 3.8. I remember. All right. So 3.8. Meth means how many carbons? Anybody? One. Okay. Meth means one carbon. Remember, F means 2. Prop means 3, and then bute means 4, and then from there it just goes in order. 5 would be penta, 6 would be hex, 7 would be hept, 8 would be octa. You get where I'm going with this, okay? It's the same prefixes 5 through 10 as you would normally use. In organic, the prefixes change just for the carbons, okay? Meth, F, prop, bute. And then this ane at the end means that all of the bonds in this molecule are single bonds. Okay, so to get the number of carbon, to get the number of hydrogens, we do the number of carbons times 2 plus 2, where N is equal to the number of carbons. So how many carbons do I have there? 1. So 2 times 1 is 2 plus 2 is 4. So how many hydrogens do I have in methane? 4. Okay? Just a little organic reminder for you. Okay? So we've got
You said
4.
N is the N
Okay.
is the number of carbons, right?
Huh?
N is the number of carbons.
Yes, it is the number of carbons plus 2. Okay? So there we go. So that's how we get CH4 with methane. So let's think about this. If we draw out methane, I say that's what shaped molecule? Tetrahedral.
Tetrahedral.
So all of these bond angles are what?
109.5.
109.5 degrees. They're all at 109.5. So, if it's tetrahedral and they're all 109.5 degrees, we would assume that all of these carbon-hydrogen bonds are the what?
Equal.
They're equal, right? They're the same because they're all 109.5, so there's nothing different that's distinguishing one from the other. But does that make sense?
Yes.
Because carbon's valence electrons come from the 2s and the 2p orbital. So that means I would have a 2s bond and 3 2p bonds. Should all the bonds be the same then? Are they the same energy?
No,
Is 2s the same energy as 2p?
absolutely not.
Absolutely not. Okay? So it looks like we should have 2 different bonds. We should have 3 2p 1s bonds and 1 2s 2p bond. Okay? So it looks like we would have different bonds. However, when we do experiments, it is shown that methane has 4 identical bonds. So that means something's up with our model. Okay?
Uh-oh, we need to
Something's
mark
up that we can't explain, so we go into the valence bond theory. And the valence bond theory is all about hybridization. So let's talk about what a hybrid is. What is a hybrid? A mix between 2 substances. For instance, the animal called the liger. A liger is a hybrid. What's a liger a hybrid of?
Human and a tiger.
A lion and a tiger. Okay? We get a liger. Like a mule. A mule is a hybrid animal. What's it a hybrid of? A horse and a donkey. Okay? So they are hybrids. We have hybrid cars. Why do we call them hybrid cars?
Electric gas.
Because they run on gas and electricity. Okay? So hybrid just means, excuse me, gentlemen. All right? Hybrid just means we take 2 different substances and we combine them. Okay? So here's our theory. We know that there is going to be an orbital overlap between the 2 atoms. To get them to bond, it means their electron orbitals are going to overlap. Whether it's an S with a P or a P with an S or a P with a P, they're going to overlap. Okay? A maximum of 2 electrons of opposite spin can be in the overlapping orbitals. So Pauli exclusion principle still holds true. I can only have 2 in the overlapping region, and they have to be in opposite spin. So 1 up arrow, 1 down arrow. Right? Right. That's all that means. Remember, opposite spins just means when I draw them out, do I draw them going up, up?
No.
No. Okay?
Lord, no.
We only draw them going up, down. We have to show that they have opposite spins. Okay? Because the orbitals are overlapping between the atoms, the pair of electrons within the overlap is going to be influenced by both of the nuclei, right? Okay? Because they're going to be between the nuclei, which means the electrons are going to be attracted to both of the nuclei, and that's why we get a bond. Okay? What do I mean by that? I mean, if we look at this carbon-hydrogen bond, so this bond right here is because one of the orbitals from hydrogen has collided with the orbital from carbon. Do we see that? Okay, they've collided together. So now the 2 electrons, we'll just draw an up down arrow, that are between this carbon and this hydrogen are being pulled by both the carbon and the hydrogen, right? Because they're between them. So that's why a bond has formed, is because the electrons between them are attracted to both. So it kind of keeps both of them together. Does this make sense? Yes?
It's like a magnet.
Okay. All right. So, as the overlap increases, the strength of the bond is also going to increase. the strength of the bond is also going to increase. Okay? But now remember, we can't let the two atoms get too close. Why can I not let the two atoms get too close?
Because it'll explode.
Why can this carbon up here, there's the carbon, there's the hydrogen, because I've drawn all over it. Why can this carbon not get too close to this hydrogen?
They'll repel.
Because they'll repel, right? Because both the nuclei are what charge?
Positive.
Positive, okay? So we want them close enough to where their electrons are attracted to both, but we want them far enough away that they won't what? Repel each
Yeah,
other,
so there's like an electron wall if they go between the two.
okay? So remember that? We did that graph with the hydrogen where we said if we're too far away, we're not attracted. If we're too close, we repel. So we want to be that minimum distance apart without repelling, okay, to make the bond. Then we talked about two different bonds, and the first one we're going to talk about is the sigma bond. Okay. Now, a sigma bond lets me know there's what kind of bond present. Single. Or if there's a double bond, that means I have
2 sigmas.
one sigma,
1 sigma, 1
one pi. And if I have a triple bond, that means I have 1 sigma, 2 pi. But remember, there's always a sigma.
Absolutely.
Always. Okay? A single bond is just a sigma. A double bond is a sigma and a pi. A triple bond is a sigma and 2 pi. That's a review. We're going to go over that again. Don't worry, it's written in the notes. Okay? So, what we're going for here is, what is a sigma bond? What makes a sigma bond? It's either an overlap of two s orbitals, or it's an overlap of an s and a p orbital, or it's a head-to-head overlap of p orbitals. Now, what do I mean by head-to-head? I mean, remember how, let's look at this picture down here. Okay, here's an s orbital, because an s orbital is the shape of a what? Sphere. And then remember, p orbitals are in the shape of the little dumbbells, right? So remember, I can have the dumbbells going side to side on a plane. I can have them going front to back. This one's coming out at me. Or we can have them going up and down. Remember that? Yes. So in order for me to get a sigma bond, like let's say if we take this one going side to side, another p orbital would have to come along and it would have to meet it head on. Does that make sense? Okay? I can't have them meeting, like see how this one's going up and down? Right there? I can't have them meeting like this. Is that a head-to-head collision? No. Okay? This right here, this is what gives you a pi bond. Okay? But do we see how this is head-to-head? Okay? So this is what gives me the sigma bond. See it? See.
They would ask us something like that. Like, will they ever ask us, like, why does it give you a sigma? Or does it, you know?
They're not. Literally, the only thing they're going to ask you is to identify the hybridization. And I'm going to show you that in just a couple minutes. And you're going to be like, okay, well, if that's all I have to know, I'm good.
Okay, this part's the part that you said we don't need.
Yeah. You don't necessarily have to get. The only thing is, if you get it, it just makes a little bit more sense when you're talking about it. You're like, oh, okay, I can see where that came from. If you don't understand where it came from, you just know how to get it. You still know how to get it. You just don't know a clue about what it means. Okay? So, this is where we're going to get our hybrid orbitals. So hybrid orbitals is when we get a blending of atomic orbitals to create orbitals of intermediate energy. Okay? So what do we mean by that? Again, we talked about how methane is tetrahedral, so all of these bond angles are 109.5 degrees apart. So that means all of these bond angles are identical. How? Okay? Well, look, here are the orbitals for carbon with no bonding. Okay? We have an up, down in the 2s, and we have an up, up in the p, so we've got one orbital that doesn't have any electrons in it, right? One suborbital. You see that? And these are just hydrogen's valence electrons. This hydrogen is 1s2, 2s2, 2p2. But remember, what are the only electrons that are involved in the bonding? Valence electrons, right? So I'm only concerned with the 2s and the 2p here, right? You still with me? Yes? Okay, so That means hydrogen has got s and p orbitals to bond with. Now, these are at different energy levels. Do we see that? 2s is a lower energy level than 2p. Correct? This line right here shows the energy is doing what? Increasing. So the 2s is a lower energy than 2p. So if carbon bonded just the way it was as a regular atom, we would have bonds that would have different energies, and they wouldn't be identical. So what carbon does when it bonds, so we see here's the S, P, P, P. When carbon bonds, it morphs this S and this P into a new orbital called the sp3 orbital. So all it does, hybridization just means we take two things and we do what? Combine them. So all carbon did was it took the s orbital and it took the p orbital and it did what? Combined them. Okay? Notice the energy level of the sp3 orbital. It's greater than the what? The 2s, but it is lower than the 2p. So the energy level is somewhere between the two. Would that make sense? Yes. So now my electrons are going up, 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 up. Do we see this? So not only did I get to decrease my 2p, which is energy payoff, I want to be at the lowest energy level possible, right? But I also managed to do what here?
You get rid of that electron repulsion.
There you go. I got rid of the electron-electron repulsion.
Now, like, is carbon the only one that can do that?
No. We're going to talk about that. No. Everybody does this when they bond. Everybody. All atoms hybridize when they bond. Okay? Now, why does this make so much sense? Because remember, we're talking about a CH4. So how many bonds am I trying to form? 4. I'm trying to form 4 bonds, right? So now, hydrogen only has how many electrons to share? 1. So now hydrogen can share an electron here, and here, and here, and here. And now all of my bonds are going to be identical. Do we see this? So now it took the shape of these s and p orbitals and it morphed them into something that looks more like this. So now all of my bonds are the same. We see it? So, your question is, I know, that's great, wonderful, you tried to explain it, I still don't get it, and I'm looking at it cross-eyed. How would I get this answer? So if they gave me CH4 on the AP exam, they gave me the well, they told me to draw it first, because that's probably what they told me to do. They told me to draw CH4, so I drew it out. Then they asked me for the shape, so I said, oh, well, that's easy, just tetrahedral. Okay. Maybe they even asked me for the bond angle, and I said, oh, that's easy too. That's 109.5. And then they said, what's the hybridization of this molecule? And I said, crap. I don't remember the S, the P, how did it
It's alright,
combine?
'cause you already got
I
the
don't
points.
remember.
Who cares?
No, this is what I do. Okay? I go, how many areas of electron density are around that carbon? 1, 2, 3, 4. So it's S, that counts as what? 1, because how many can I have in an S? Just 1 suborbital. How many suborbitals are in a P? 3, P, 3. 1, 2, 3, 4.
That's hard.
No, I'm gonna forget how to do it.
No, you're not.
But it's alright, because we already got 3 points.
All you do is count the areas of electron density. That's all you do. So let's imagine, I'm jumping ahead for a second, but it's okay. So let's imagine we had sulfur and it had 5 fluorines around it. Okay? So how many areas of electron density are around this sulfur? 1, 2, 3, 4, 5, right? So the hybridization would be S, that's 1, P3, that makes 4. What comes after P? So the hybridization of this one would be sp3.
This is all we're doing.
You don't use S again?
Why not? Why would you not just put S, P, D, and then?
Because I can't have 2 S's in one energy level. I can have 3s2, 3p6,
So that'll
3d
be like-
something,
That's a high.
but I don't repeat s again in like the third energy level.
What's the biggest you'll
So you're
do?
just doing them for the valence load.
The most I could get would be if I did something that had 6 bonds to it. So then it would be sp3, d2.
So it's always gonna be S regular and then P.
Something. And then sometimes it's like, what if I did something? Well, we're getting ahead of ourselves. We'll come back to this. All right, now it also works with something like ammonia. Ammonia is what? NH3. So I would draw that with the lone pair. You should know how to draw ammonia right now. Should be standard. All right, so there's my ammonia. You have to count your electrons as an area, your lone pairs as an area of electron density.
75.
So I say, how many areas of electron density do I have here? Nope, the pair just counts as one. So 1, 2, 3, 4 areas of electron density, right? So what would my hybridization here be?
SP3.
So most of the time it's gonna be SP3.
No.
Well,
Sometimes it's going to be SP2. And sometimes it's just going to be
Well, how do you
SP.
get an SP2?
That's what we're going to be going over next.
Okay.
Does everybody see this one then? We got that. We understand how I got it. Okay. But what happens when I get those pesky multiple bonds? What happens when I get a pi bond? When I get those double and those triple bonds. Okay? Now, remember we said sigma bonds come from a head-to-head overlap, right? Okay? Pi bonds come from a sideways overlap. Okay? Another thing for you to remember is pi bonds never occur without a sigma bond first. So before I ever have a sideways overlap, I'm always going to have a head-to-head first. Okay? Sigma bonds. There's the signal for sigma. Sigma bonds only happen from hybridized orbitals. This is important for you to get, for you to understand the next concept we're going to talk about it. Pi bonds happen from the unhybridized orbitals. So sigma bonds happen when they're hybridized. Pi bonds happen when they're not hybridized. And remember, we can only make double bonds with carbon, nitrogen, oxygen, phosphorus, and sulfur. Those are the only 5 elements that can make double and triple bonds. CNOPs. They're the only ones. Nobody else. So if you try to make a double bond with anybody else, you are wrong. Okay? Don't do it. Alright. Now, notice, in CH4, when we hybridized, all 4 of them hybridized. Do we see that? My S and all 3 of my P orbitals hybridized. Everybody see it? That means we had all single bonds, right? 1, 2, 3, 4 single bonds. 1, 2, 3, 4 hybridized orbitals. Do we see that? Yes, we see that. When we have a double bond on something like ethane, that would be C2H4. So I would draw it C double bonded to C, H, 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 H.
Why is SC not in that group? All the other ones are like non-metals, so
Why is what?
SE. You know, like all the other CNOPs, they're all non-metals.
Selenium? I'm not sure. It's probably because your valence electrons are just so far away from the nucleus at that point that it's hard to get an increased area of electron density. Is what I would assume, but I don't know that at all. That's just a random chemistry guess.
So, oh yeah, they're all non-metals that are like soft.
Yeah.
Oh, that's not.
I don't know. Well, fluorine, chlorine, and bromine are non-metals too.
Oh, yeah. But they're not red.
Yeah, I'm sure.
That's what counts.
All right. So C2H4, and so then we saw here where we have to draw it. Now notice, regular carbon here, we still have the 1, 2s orbital and the 3, 2p suborbitals. Do we see that? Same as always. Except this time, notice that we only hybridized how many of them? 3. 1, 2, 3.
It's,
Yes.
I don't
Okay.
remember my
We
comments.
only hybridized 3 of them. Notice this 2p orbital here. Did it change? No, it's still the same one. Same energy level and everything. Did we see that? So we only hybridized 3. We didn't hybridize the last one, which means in this molecule right here, I'm going to have 3 sigma bonds and I'm going to have 1 pi bond around the carbon. Can we prove it? I'll prove it. Okay? Now, this carbon to hydrogen bond here is what kind of bond? Single, double, triple? Single. So that means that's a sigma bond, right? Okay? This carbon to hydrogen here is a single bond, so it's also a what? Sigma. We said with double bonds, we get what? 1 sigma and 1 what? Pi. So here's a double bond, so I've got 1 sigma, 1 pi. The sigma bonds all came from what? My hybridized orbitals. My pi bond came from this orbital that was not hybridized. Okay? How do I see that in a 3D picture? Here we go. So here's my orbitals. Everybody with me? So here's my carbon to carbon, which is double bonded. Right here. Here's my double bond. And then here's my carbon to hydrogen, carbon to hydrogen, carbon to hydrogen, carbon to hydrogen. Everybody see that? Then my double bond is in the middle. Okay? So here's one of my sp2s where I have a head-on collision between the hydrogen and the carbon orbital. Do we see that? Okay. Here's the other one, head-on collision between the carbon and hydrogen. And then here's my sigma bond out of that double bond where the p orbitals of these 2 carbons are colliding head-on. Does everybody see it? They're definitely colliding head-on. Now, if we take away the hydrogens and pretended like they're not there, we get this picture. Okay? So notice, this is just showing the double bond between the carbon and the hydrogen. Okay? This part of the p orbital is colliding what? Head-on. So there's my sigma bond. Okay? These 2 are what? Side to side, right? So this is where I'm going to get my pi bond. And the pi bond overlaps on the top and the bottom.
Oh, so it has nothing to do with the double bond. It has something to do with those other 2.
Yes.
That's weird. Kind of bad.
Well, what do you mean it has nothing to do with the double bond?
Well, like you're saying, like the pi bond is coming from both of those p orbitals, but I can't get over.
She had to take a call, guys.
Hey, y'all just want to text me what ask me to text you. Alright, so what they say?
They just put me on some
Is everything okay at time?
I mean,
Is it normal?
it's really.
So I was worried about.
Is it truly bigger than everybody else's?
No, it's not, it's just my brains.
All right, we good?
Jeff took over.
Sorry, Hopeful. Had a phone call. So, again, am I necessarily concerned that you know all of this? No. Here's what I'm concerned with. Okay? I have C double bonded to C with the H, with the H, with the H, with the H. And I ask you, what is the hybridization of this molecule? All right? So I pick a carbon. I'm going to go with this carbon. Everybody see that carbon? And I say, how many areas of electron density are around this carbon? And before you say 4, double bonds only count as 1 area. Okay? So that means there's 1, 2, 3 areas of electron density around that carbon, right? Yes? So I go 1, 2, 3 areas of electron density. So what's the hybridization? sp2. Did you see that?
Very exception.
No.
Don't
No
let it lie to you.
exceptions. No, there are really no exceptions to this.
I'll believe it when I see it.
So the only other type there would be is if I had a triple bond. So in this case, if I had something like C2H2, which is ethine. Anytime I see the ine, it lets me know that my carbons are triple bonded. When I see the ene, I know they're double bonded. When I see the ane, I know they're single bonded. Okay. So, how many areas of electron density are on this carbon?
Two.
2. 1, 2. So what would be the hybridization here?
SP.
SP. Do we see that?
Oh,
Okay. Remember, with triple bonds, I have what? 1 sigma and 2 pi bonds, right? Okay. Why did that? And then I've also got a sigma right here. So overall here, I've got 2 sigmas, 2 pi's. Does everybody see that? Where did that come from? Remember, I've got these 4 in a regular carbon. What happened was 2 of them hybridized. That's where I got my 2 sigma here and here. And then 2 of them did not, and that's where I got my 2 pi bonds. Okay? Am I concerned that you necessarily understand all of that? Let's start with exercise 1. Describe the bonding in the ammonia molecule using the localized electron model. I'm not necessarily concerned that you can do shapes right now. I just want to focus on hybridization. Okay? Yes. So let's talk about ammonia. Let's draw it. We know it. We love it. We got it. Okay? All right. How many areas of electron density are around that nitrogen? 4. 1, 2, 3, 4. So the hybridization is
SP3.
sp3. If I did ask you the molecular shape of this, what would you tell me?
No, it's
Trigon planar.
Trigonal pyramidal, right? Okay,
Oh, yes.
trigonal pyramidal. All right. Now, if I asked you the electron geometry, what would you tell me? Tetrahedral, because there's 4 areas. Yes. All right.
Yes.
Exercise 2 says describe the bonding in the nitrogen molecule N2. Here's what it looks like.
Let's see, 2 areas.
SP.
So how many areas of electron density around this nitrogen?
2.
2. 1, 2. So the hybridization would be
SP.
sp. And if I asked you for the shape of this, you would say it is linear, because it's only 2 molecules. There's only one shape it could be. Alright, exercise 3 asks me to describe the hybridization in the triiodide ion. I'll draw that for you. There you go. So let's look at the central. You always look at the central atom to describe the hybridization. What's the central one here? The iodine. Trick question. All right. So we're looking at the one in the middle. Okay. How many areas of electron density are around the iodine in the middle? 5. Right. 1, 2, 3, 4, 5. Does everybody see those 5? So what's the hybridization?
SP3D.
sp3.
That's a trick question.
I know, they write D first. I don't. It doesn't make sense to write D first.
We've always been taught SPD.
SPD, there you go. It really doesn't matter. They are fine with it either way. Everybody see it? Yes? Easy? Alright, and then exercise 9 says how is the xenon atom hybridized? I'll draw xenon for you. Xenon tetrafluoride.
Isn't that where it's got 2 little? No, that's yeah.
Yep.
Okay. SP3D2.
There you go. How many areas of electron density around that xenon? 6. So my hybridization would be
SP3D2.
yay.
Knowledge.
Knowledge. Alright. Exercise 5. If we draw CO, It looks like that. What's my hybridization of this gonna be? SP. Does everybody see that? We understand why? 2 areas of electron density around carbon or oxygen. You can choose either one. Because in this case, either one is technically the central molecule. Those are the 2, right?
So it doesn't matter, like, if it's a double, single, triple.
No. This still just counts as 1 area of electron density. So there's 1 area here, 1 area there. So 1, 2. Okay. We draw BF4 negative. What's the hybridization there? SP3.
Is it ever gonna go past SP32?
No. Never.
SP3D.
SP3D. 1, 2, 3, 4, 5. Everybody see that?
We just have a little test just on that.
I don't know, I'm not very good at drawing. So it's
All right, quiz time. Clear off your desk with everything except something to write with.
Teacher's gonna be on their hands.